are you today? Great. This conversation is going to be about updates in progressive addition lenses. There is a lot of talk around the optical field about progressive addition lenses, freeform technology, digital molds, and aberration and distortion control. And there can be some confusement in regard to what categories of freeform different technologies fall into. So the goal of this conversation is that we make freeform technology a very easy subject by looking at all of the different categories so that when we have a representative from a lens manufacturing company come in to talk to us, we'll have a clear understanding of exactly what technology they are introducing to us. Progressive addition lenses have quite a history in regard to evolution in design. The very early designs, way back when, in the late 70s and the early 80s, the first generation of progressive lenses had this ratio of 4:1. What this 4:1 ratio means is that the aberration and the distortion on the outside of the lens is 4 times that of the add power. So when we look at contour plots, typically they are a +6 base curve with a plano with a +2 add. That's a typical contour plot. So if we look at this first generation 4:1 ratio here, generation 1, years ago, we were talking about a 4:1 ratio of distortion to add power. So based on a plano with a +2 add, there were 8 diopters of aberration and distortion out here in the periphery of the lens. It's no wonder our patients and clients complained about all of the swim and the fishbowl effect that they experienced on the outside of their lenses. And then there was a big jump in advancement, generation 2, where the ratio of distortion was 2:1. So, given the same example, a +6 base curve with a plano with a +2 add, there is twice the amount of distortion compared to the add power. So 4 diopters of unwanted aberration and distortion in the periphery based on a plano +2 plot. Then, years later, the next generation came out, which is very exciting, which is this generation 3, which is a 1:1 ratio. Here's what that means. Based on the same example, a +6 base curve with a plano +2 add, the amount of aberration or distortion out here in the periphery would be equal to the add power. So with the generation 3 1:1 ratio of distortion to add power, given the fact that the add power and the distortion are equal, there's a 50-50 chance that the brain is either going to go directly to the near point area or out here to the periphery where the aberration and distortion is. Now we are up to generation 4 and even generation 5 in regard to controlling distortion to add power. And you can see that in this example, plano +2 add, we only get 1.5 diopters of aberration. Each color represents a half a diopter. So from the yellow, a half a diopter, to the green, 1 diopter, to the light blue, 1.5 diopter. We have a situation where the distortion is a half of a diopter less than the add power. So the brain normally wants to go to the strongest area of the lens. The brain naturally goes to the steepest curve on the surface. That's why years ago, when we had a 4:1 ratio of distortion and even a 2:1 ratio out here in the periphery of the lens, the brain went right there because it was a steeper curve, a stronger power. With the 1:1 ratio of distortion to add power, there's a 50-50 chance that the brain goes to the near point or out to the periphery and sees the distortion. With a half diopter less than add power ratio, and now with lower add powers, we're actually up to a 0.75 diopter less than add power ratio. Now the curvature and power out here in the periphery of the lens is less than the add power here at the near point range. And so the brain ignores this. It exists, but the brain ignores this. And to understand plots better, I'm going to go over and make a diagram To understand plots better, it's helpful to understand the zones of the progressive lens. Now, in dispensing theory 2 earlier, and in your clinicals and in your dispensing lab 2, we look at the markings for progressive lenses. We look at the fitting cross that goes directly in front of the patient's pupil. We look at the prism reference point below the fitting cross, and then there are markings from the manufacturer, laser markings, and then the near point circle. If the nose is here, this would be for a right lens looking at the patient. These are also made up of zones. Zones in regard to the area of the lens. We have zone 1, zone 2, zone 3, and zone 4. Zone 1 is the distance prescription. Zone 2 is the intermediate or arm's length area of the lens. Zone 3 is the near point for reading. And zone 4 is the periphery. Lens designers and engineers and manufacturers have a choice. They can put the aberration or distortion below the 180 or above the 180. We have no choice but to put the distortion or aberration in zone 4. We can't put the aberration and distortion in zone 1 because that's for distance vision. We can't put the distortion or aberration in zone 2 because that's necessary for intermediate. We can't put it in zone 3 because that's necessary for reading, so we must put it in zone 4. So the ratio of distortion to add power is the amount of aberration or distortion out in the periphery of the lens and how the manufacturer and designer deals with that distortion. All lenses, progressive addition lenses, have aberration. If they focus to 20 feet, and if they focus to intermediate, and if they focus to near 40 centimeters or 16 inches, there will be aberration and distortion. It's a mathematical fact. It's the laws of physics and lenses. So there's no such thing as a lens that will be wide, wide, wide in the intermediate zone 2 for computers if it also has 20-foot vision. And so we have to decide with our patients and clients what kind of lens design will be best for them and will best serve their needs. So this shows a topography of the old progressive addition lenses, and all of these colors represent a half a diopter of aberration and distortion each. So this 4-to-1 ratio has 8 diopters of aberration. No wonder people didn't like them. And then 2-to-1 ratio. By the way, we don't have any more generation 1 lenses on the market today. However, we do have generation 2. Generation 2 has a 2-to-1 ratio distortion, which is still a very, very poor design. I make a really bad joke saying somebody's got to sell a progressive addition lens for $39.99. And so when we see these kinds of things out there in our marketplace, it's very old technology, it's very old generation, and it has double the distortion out here in zone 4 than the add power, and the patient isn't going to have as positive of a visual experience. And then again, big jump in technology, a 1-to-1 ratio of distortion to add power, and finally the lens engineers have figured out a way to get the distortion below the add power. Again, the brain is going to go to the near point circle and not out to the periphery as much. When our patients and clients complain about aberration or distortion in their periphery with progressive addition lenses, we have 3 magic adjustments we can do to help them. And this is also covered in dispensing 1, adjusting the frame in Chapter 9 in Brooks and Borish textbook. But basically, if we think about distortion as being like a windowsill, and if the windowsill is out here, and I can see this distortion or aberration in my field of view out here in my periphery, our magic adjustments are decrease vertex distance, increase pentoscopic tilt, and increase parabolic curve or face form or wrap. Here's why. If this is the distortion or aberration, and I decrease the vertex distance, and I increase the pentoscopic tilt, and I increase the parabolic curve or face form or wrap, what happens to the aberration now? It still exists in the lens, however, by bringing the lens closer, tilting it, and wrapping it, it puts the aberration and distortion outside of our line of sight. And so to the patient, it's as if it disappeared. So when in doubt, decrease vertex, increase tilt, and increase wrap, and you can troubleshoot a lot of visual complaints just by using those 3 adjustment techniques. So as I mentioned earlier, there is a lot of discussion in regard to freeform optics. What is freeform? Previously, semi-finished progressive edition lenses were required for manufacturer to use ceramic molds. So here's how it has been up until now. First, the lens design software. The lens designer, lens engineer, wakes up in the middle of the night and says, "Why, George, I think I've got it." And from that, he creates or she creates an algorithm. And the algorithm is a very high mathematical formula that they actually run through supercomputers. It's 4th order math, polynomial equations. I have no idea how to do that kind of math. It's very high-tech math, and they have a design. And we see that design as the contour plot with the curvatures and depths. From that design, from the original concept, from the designer, the lens engineer, they would create a ceramic mold. From the ceramic mold, they would then create a glass mold. And so the design is on the front of the glass mold, the progressive edition design, zone 1, zone 2, zone 3, and zone 4. Then they would insert or inject liquid plastic, if you will, polymers and monomers into the mold. And then they would surface off the back surface. They would make one spherical cut for sphere distance. And if the patient has astigmatism, they would make 2 cuts. Remember we learned about toric base curve and cross curve in lens theory 1? Toric base curve and cross curves are the curves used on the back surface to correct for astigmatism. So the entire mold is here, and the design of the lens is all in the front mold. And that means everybody gets the same design. And we customize the back for their distance prescription, sphere or sphere and cylinder and axes. But here's the thing. Myopes converge differently than hyperopes. When we converge down and in to read, a myope needs a different design than a hyperope. An emmetropic presbyope, plano plus 2 ad, needs a different design than a high hyperope or a high myope. And so in fact, the designs were limited in that we had a mold which covered a range of prescriptions. So I'll ask you a question. Have you ever had the misfortune to take statistics? What? I can't hear you. Well, I did. That course really gave me a run for my money. That was a tough one. I learned 2 things from statistics. 1, don't gamble. The house always wins. 2, whenever I hear a piece of data, I think bell curve. Did you know that 92% of statistics are made up on the spot? Ha ha ha. It's a lame joke. Okay. So I think of a bell curve. Here's an example. Presbyopia begins at the age of 40 to 42. Bell curve, 1 person fits perfectly into that piece of data, that statistic. 80% of the people are pretty close. 10% are here, and 10% are here. Some people become presbyopic at the age of 36, 38. Some people never become presbyopic. It depends on how much collagen we have in our bodies. I had one student ask me years ago about her grandmother. She said, my grandmother is in her 80s, and she does needlepoint. She can read the paper. She can read the phone book. Years ago, we had phone books with paper, with phone numbers printed in them, in very small print. And she said, my grandmother can read the phone book, she can read the newspaper, she can do needlepoint, and she doesn't wear anything for reading. And she wondered, why is that? She was expecting some kind of exotic answer. The answer is bell curve. Her grandmother happens to be way out here in the outlying areas where she never became a presbyope because, luckily for her, she had collagen production more than normal her whole life. So when it comes to a lens design and a mold for distance, near, intermediate, and periphery, when it's in a mold, it's a bell curve, and only a percentage of our patients get perfect vision from that. So from this, we figured out how to eliminate the ceramic to glass copy process, and that will come up in a moment. So what I just described is a standard progressive edition lens. The front surface is cast from a glass mold made from a ceramic mold. And when you see this little piece right here, that doesn't mean it's the segment like a bifocal. It represents where the design is on the front surface of the lens or on the back surface of the lens. And then the back curve was a normal back RX. Any generator who could create an XY, meaning in one plane, file for sphere and cylinder correction for distance vision. And this is done through rubbing surfacing. So now we have a technology known as direct surfacing equipment, where it is a diamond lathe that cuts into the surface. And the difference here is it doesn't only cut back and forth, up and down, it can cut in and out. So there's an X, Y, Z cut going on. And we'll talk about that in a little bit more detail as well. And with the freeform generators, we can have laser markings and custom engravings. You could put your company logo on it if you wanted in that regard. So here's the conversation. Freeform technology is described in many different ways, but the truth of the matter is this. Freeform is a method of manufacture. It's a machine. It has nothing to do with design. If the design was poor, like a 2-to-1 ratio of distortion from a front molded version, bringing that to the back surface through freeform technology is not going to make it better. It's just going to be a bad design on the back surface. So the categories for freeform technology, what I would name would be a digital mold or freeform optics and back surface freeform. So in this case, the designer has figured out a way, and through manufacturing, how to skip the ceramic to glass copy process, and the lens design software goes directly to the mold. And that's better, because every time we duplicate something, it does lose its original integrity. However, it's still a mold. And so if a manufacturer says to you, this is freeform, my question to them would be, great. Is the freeform technology applied to the mold or to the back surface customized in the lens? It's a big difference, isn't it, right? So we want to be very clear in what we're talking about. And I'm trying not to become an optical snob, but I just have to say, when I hear molded lenses, the first thing that comes to my mind is molded lens, molded progressive lenses. Prefab, off the shelf. One size fits some. But by bringing the optics to the back surface completely through freeform technology and design, we can put every single patient and client in the very center of that bell curve, because each and every one is designed for them. Their prescription, their refractive error, the shape and size of their frame, the vertex distance, tilt, and wrap properties are all incorporated into the software program, and the design is made just for them. much different than a molded product. So then we go into another level of freeform optics where the front is still a mold, but it is digitally cast. In other words, no more ceramic to glass copy. It is directly applied to the mold from the freeform machine. It's still a molded product though, and the design is still on the front. And in the back, the same thing, X and Y cuts, which is sphere or sphere and cylinder for their distance prescription. But their intermediate and the corridor length and the corridor width and the near power width and the add power length is all standard and all the same. Direct lens technology means still having a front molded product where it is digitally applied to the mold versus ceramic to glass copy, but then on the back they have X, Y, Z. X is back and forth, Y is up and down, and Z is in and out. Now that we can cut and create this in and out cut, we can create curvature and depth. And if we can create curvature and depth, we can create a surface, a lens surface for progressive addition lenses. To give you an idea of how high-tech this technology is, let's look at the very basics. A single vision sphere has two curves, a base curve and the back curve, ocular curve. A cylinder single vision lens has three curves, the base curve on the front, the toric base curve and cross curve on the back for astigmatism. A cylinder bifocal has four curves, segment curve, base curve, and then the two curves for the back. So we're talking about lens designs with 3 or 4 curves. Today's highest technology progressive lenses made through freeform design with computer software compensation has up to 3,600 curves on a single surface. 3,600 curves. It's a very intricate design, and because of that, the fitting criteria is much higher as well. So continuing on, then we evolved to a dual ad progressive addition lens, where they put half of the ad on the front and half of the ad on the back. When we bring the optics to the back surface, we increase the field of view. And so the whole idea of the dual ad progressive was to split the ad between the front and the back surfaces, which does in fact widen the field of view at near. However, it does nothing at distance and intermediate. It's the same mold prefab kind of design. Through personalized freeform and digital medium, we can personalize the design for the patient or client. Here are some examples. A truck driver needs to have a progressive addition design which has a completely wide edge-to-edge field of view for distance, and their near area needs to be lower because their main objective is to see in the distance while they're driving. An accountant or a bookkeeper is going to require more intermediate for the computer monitors and near for their numbers, bean counting, I shouldn't say that, for their bookkeeping and accounting, and not as much distance perhaps for on the job. Through customized freeform technology, we can design lenses for all kinds of purposes. We can design a lens for a pilot who needs distance, near, and then another near area so that they can look up and see their controls. We can design a lens for golf, where distance zone 1 is distance but angled down for the green. Zone 2 is not intermediate. Zone 2 for the golf lens is down where the ball is. Zone 3, the reading for a golf lens is a tiny, tiny, tiny speck of reading where the golfer would lift their head just to be able to fill out their scorecard, and then 4 is still the periphery. If we wanted to design a freeform, personalized digital lens for somebody who rides bicycles or motorcycles, they don't really need 20 20-foot vision like the truck driver. What they really need is a safety zone around them, 6 to 10 feet. And so we can readjust the design so that they don't have 20-foot vision, but they have in zone 2, intermediate, wide, 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 like a safety bubble, if you will, because it's crucial that they see cars beside them and closely in front of them. If we were to design a lens for computer use, if somebody has one widescreen monitor on their desk or 2 monitors on their desk, we can completely ignore 20-foot distance, and because we ignore 20-foot distance, we can spread the intermediate out so that they can see their wide monitors with a full range of near to intermediate distances, but they're not suitable for driving. So what we're learning in opticianry is that there are so many uses for task-specific progressive lenses, and we can't do that with a mold. We must do it through freeform digital technology so that we can personalize it. In this case, the entire design is put on the back surface of the lens, incorporating the patient's prescription, PD, fitting height, frame dimensions, vertex distance, tilt, and wrap, all incorporated into the formula to make it just for them. This illustrates how bringing the surface, bringing the design to the back surface increases field of view. And this diagram represents on the front, the blue would be a front surface molded design. And then the red on the back represents a back surface freeform personalized design. And if we did ray tracing from the front to the back to the eye, we would see that there's a great increase of field of view, sometimes up to 30% field of view increase. Think of it like the keyhole effect. You know, in the old movies in the medieval days, and castles had keys with keyholes. So if you get real close to that keyhole, i.e. closer vertex distance, you have a wider field of view. And if you walk far away from that keyhole, the field of view shrinks. You can think of it like being on a ship with a porthole. If you're far away from that porthole, the field of view is going to be smaller. But as you get closer to the porthole, the boat window, the field of view increases. So bringing the optics to the back surface increases field of view. Now this slide looks quite complicated, and that's kind of on purpose, to make it look complicated just so that we can simplify it so that it makes optical logical sense to you. So in this first example, we have a regular conventional progressive with the design on the front and the normal back surfacing procedures. Then we have front freeform optics, which I would not call freeform. I would call it a digital mold, because that's what it is. To me, when I use the term freeform, I keep it only for back surface, 100% back surface, personalized design. However, some manufacturers call this freeform when in fact it's really the mold that was made digitally. They got rid of the ceramic to glass copy process and put the design directly onto the mold. And then we have that same idea of a direct digital mold, but on the back they did use the XYZ cuts, which is back surface aspheric. So if we use asphericity for the front, because we call it aspheric. If we bring asphericity to the back surface, we call it atoric. A lot of opticians don't know the difference between that, so you'll often see in different publications aspheric and atoric as the same, but if it's on the front, it's aspheric. If it's on the back, it's atoric. And then we went into dual add, where they put half the add on the front in the design and half the add in the back through freeform technology, which widens the field of view at near for reading, but not for everything else. And finally, direct technology, aspheric, atoric, completely back surface design that we can also personalize for different viewing tasks. That's the highest level of freeform technology. So, more types and counting. We begin with a semi-finished lens blank. So we take a semi-finished lens blank and it could end up being a plano sunglass. It could end up being a single vision sphere. It could end up being a single vision cylinder, or it could end up being a back surface progressive edition lens through Freeform with up to 3,600 curves. So they're very, very different animals in regard to the quality steps. And so again, this just kind of gives us a recap. Design on the front using digital cutting. Half the design on the front, half the design on the back, and then all of the different designs on the back with different purposes, near to intermediate with more near to intermediate power here for like computer use, or a very low ad for truck driving, etc. So all of these different purposes. And then to raise the bar even higher, we as opticians have the ability to work with the lens designs, and we can do a higher level of customization. And that is as worn technology, also called position of wear. When we are examined by the eye doctor, and we have the refraction part of the exam, which is better, click 1 or click 2. The phoropter is farther away from the patient. The phoropter is farther away, and it is straight up and down, and it is not tilted or curved. So when the patient's in the doctor's office and they see 20/20 during the examination, we take that visual experience, if you will, the numbers that the doctor writes on the prescription pad, we take that visual experience from the refracted plane, which is farther away, straight up and down, not tilted or curved, and we bring it to the spectacle plane. In other words, where we wear the eyeglasses, and we wear eyeglasses closer, and we tilt them and we curve them, that changes the effect to the brain of the prescription. As you remember from lens 2 and dispensing theory 2, when we shift the vertex distance, here's the lens and here's the focal point, when we shift the vertex distance, the focal point shifts too. And it goes off our retina, and therefore we don't see as clearly. When we tilt a lens, it actually, to the brain, adds surface cylinder. It's as if we ground in the cylinder in surfacing. It's not in the lens. You couldn't read it in a lensometer. However, to the brain, it might as well have been cut in. And in regard to face form or wrap, it actually takes the apex of the optical center and shifts it out here, which can induce horizontal unwanted prism. A small amount, we're not talking about great amounts here, well below ANSI standards. However, enough of an amount that the patient might say, I just don't see as well through my eyeglasses as I did in the doctor's office. And the reason that is because we're changing the optical experience by shifting the lens orientation in front of the eye. So vertex distance is part of that. In addition, patients choose eyewear that is curved and tilted, definitely not flat. And this results in unintended changes to the original prescribed prescription as viewed by the patient. And that requires compensation. We know that with vertex distance, the effective power of a lens changes as the lens shifts toward or away from the eye. We sell lenses with focal points and focal lengths. And when we shift the lens, the focal point shifts as well. We don't sell zoom lenses in our profession, and so when the lens physically moves, the focal point physically moves as well. There's talk about selling zoom lenses in our profession where they have stuff inside the lens and you can touch it digitally and it can focus. And that will happen in our professional future. We are years away from that at this time, but through new technology which includes 3D lens manufacturing, which isn't out yet for the public consumption, but is being used a little bit in our profession. It's still in research at this time, but at that time, they can inject or add electronic devices for that to happen. But for now, we deal with lenses when we shift the lens, the optical, the focal point shifts as well. So we need to compensate for that. Pentoscopic tilt. The effect of tilting a lens is unwanted surface cylinder. And if we tilt a plus sphere, it will actually induce plus cylinder power. If we tilt a minus sphere, it will actually induce minus cylinder power. This is surface cylinder. It happens in space, if you will. It wasn't ground into the lens, but to the brain, it may as well have been ground into the lens, because that is the adverse visual effect that our patients get. And then finally, wrap. Average face form is about 3 to 8 degrees. If the optician doesn't give the lab these properties, then they will default to 5 degrees for pentoscopic angle and face form and wrap. So the values given, or the defaults, are then used in the calculation to revise the prescription. Sometimes students ask me, hey, can we calculate compensated calculations here? And the answer is no. They are very, very, very high polynomial fourth order math equations, and in fact, a normal computer won't even do it. They must use a supercomputer that can run very high level math with algorithms to get these values. So when the prescription comes back from the doctor, and when the lab ticket comes back from the lab, they're going to be different. So in other words, the doctor may have prescribed -2 sphere. After going through the calculations and compensations for vertex, tilt, and wrap, the number may end up being -1.92, -0.0032, axis whatever. And when the optician sees that, they might think that something wrong happened, but the fact is that is on purpose, and that is the compensation on purpose. Why? The computer software gives equal and opposite compensation in regard to the change. So by changing the effective sphere power through vertex shift, the calculations will tweak the sphere power so that it ends up being as if it were from the refracted plane. And when we add tilt, which we must, we have to add pentoscopic tilt. Otherwise, if we don't, if we fit them ortho, straight up and down, when the patient rolls their eyes down to see at near, they will be looking underneath the lens through air. So we must tilt that lens, pentoscopic tilt, so that when the patient looks down, then they're down here at the reading area. So when we add pentoscopic tilt, the unintended result is unwanted surface cylinder. So the Freeform technology computer software will calculate on purpose equal and opposite cylinder to neutralize that out. You've probably noticed by now, in optics, we fix a lot of things through neutralization by adding equal and opposite to get rid of the aberration. And then finally, with wrap, if it induces unwanted horizontal prism, it can compensate for that as well. So when you verify the lens, you're not going to expect to see -2 sphere. You're going to expect to see minus, I'm just guessing here, but we're just doing a ballpark, -1.932, -0.31, axis, whatever. So then, when you're verifying that in the lensometer, you are verifying the compensated power, not the doctor's originally prescribed RX. And then you may wonder, how do we do that with a manual lensometer? Because manual lensometers only go to increments of 1/8 of a diopter, 0.12. And these can go to a 20th of a diopter, a 60th of a diopter. How do we measure? For now, because auto lensometers haven't really come to the point yet where they need to be for really great validation. We still rely on the manual lensometers for that. So here's how you do it. If it comes in as 1.932, well, you know where the 2 line is in the lensometer on the power drum. You know where the 1.87 line is. So you just put it between them and you go. In other words, use your optical logic to kind of go in between the 8th diopter lines on the lensometer and that's how you'll neutralize to verify the accuracy of the compensated RX. So, 8 types of freeform and counting. We talked about all of the semi-finished, etc. And now we can do all of these personalized, which we also already talked about. But we also want to talk about sunwear and sport. Remember in Lens 1 we learned about base curve theory, Vogel's formula, and we learned about the fact that when we go off base curve theory, they get a lot of aberration and distortion in the outside of their lens. Well, what if somebody is a -4, for example? So -4, according to Vogel's, -4 divided by 2 is -2, plus 6 is +4. They should have about a +3.5 or +4 starting base curve. But what if they want a fashion wrap or a sport wrap that has a +8 base curve? We can't just give them a +8 base curve without compensating, because they're going to get way too much distortion and swim out here. So through freeform technology, the computer software calculates how much unwanted distortion is created by going away from base curve theory, and then they correct it all on the back surface. In our future, Vogel's formula and calculating the best base curve won't even be important anymore. In fact, we'll stop teaching it, because in the future, all of it is going to be corrected on the back surface through freeform technology. So this tells us some of the challenges we have when we want a big wrap or fashion sunwear or sport glasses. The line of sight going through the optical axis and the optical center is straight through. But when we wrap this lens, remember, light goes to the optical center straight through, but it also goes perpendicular to the surface, doesn't it? At a 90-degree angle to the surface. So here everything lines up beautifully, but when we wrap it, now the optical center is here, which corresponds with the optical axis, but the patient's line of sight, their position of gaze, is straight. What is that going to cause? Unwanted induced prism, horizontal prism. So you may see some come back compensated with a little prism in it. Why? The computer software on purpose calculates how much unwanted prism is induced by going off the line of sight, then on purpose introduces equal and opposite prism so that it neutralizes. So what happens is this: we go off base curve theory and light zigs, and then we compensate it in the design and it zags, and it zigs and zags so quickly, the speed of light, 186,000 miles per second. Our brain is amazing, but our brain can't pick up this action. So to our brain, it's as if the light ray went straight through, right to our retina, clear, crisp vision. And this is an example of a lens changing the topography and changing the design in the computer software program to compensate for the fact that the eye is way in, excuse me, nasal to the optical axis. And by controlling the design through freeform, which can only be done through back surface personalized freeform, this cannot be done in a mold. In this case, they continue twirling the design so that the eye ends up in the perfect major reference point and no aberration and no unwanted prism occurs. And then all of the different types, excuse me, I'm going to go back to this last slide, is all of the types of freeform and all of the things that we can do to compensate, and as a result, we can personalize it. We can personalize it for truck drivers, for accountants, for pilots, for golfers, for motorcycle riding, etc. And so don't be fooled. Freeform is just a machine, it's not a design. And so we as opticians need to become connoisseur of designs. We have to ask questions of the manufacturer, like, what is your ratio of distortion to add power? Where is that aberration placed in zone 4? Is it below the 180? Does it go above the 180? How can I tweak this? Or is it the same molded freeform for every single patient, whether they're a hyperope or a myope? And what are the indications of that? So the update in progressive lenses is, we've come a long way, baby, and the best is yet to come. Have a blast as you dispense the latest technologies of freeform lenses using your optical brain and your optical common sense.